Okay, I would like to continue with the density matrices by doing with you the exercise for the oscillator, okay? So, to repeat, averages of an operator on a pure state can be written as the trace of the matrix representing the operator times the matrix representing the projector on the state psi. Okay? And we said that the most general thing you can do is to actually have a certain number and row of state, psi I, supposing them to be orthogonal, and to consider sum over I of Wi psi I psi I. So this is the projector on the state psi I, and this is a weight such that the sum over I is equal to 1, okay? So if only one of this is equal to 1 and the other are 0, you recover essentially a single projector. But in more general case, this is what we will call a density matrix, okay? So an object whose trace is equal to 0, is equal to 1, but such that in general the trace of rho square is less than 1. It is equal to 1 indeed only if there is only one state present in the expansion, okay? With this, you can more generally express averages of A as the trace of the matrix representing A times the matrix representing rho. Okay? Or even even in more general terms, the trace of the operator A times the operator rho. Okay? Without even any reference to any basis. Okay. So this is what we did last time, and we claimed that quantum statistical mechanics, the canonical ensemble, is a special case where now you have, in general, an infinite number of states. You consider the psi to be the eigenstates of the Hamiltonian, okay? And the weight here to be just e to the minus en over kbt divided by the partition function, which is the sum of this thing, in such a way, okay? So z is the sum over n of e to the minus en over kbt, and in this way, the sum over n of Wn is just equal to 1. Okay? So the proposal is now to work with a density matrix. I'll write it up here. Okay? Rho, which is the sum over all eigenstates. Okay? So now this is an infinite sum. Indeed, I'm using a notation in which this is a label, which might be a composite label, as you always know. Okay, so it might be even a very complicated object. You have to sum over all eigenstates. Wn times what? Times the projector on the state psi n. Okay? Where Wn is this thing. Okay? And so I could write this as sum over n. E to the minus En over kBt over Z, the projector. Okay? Last time we argued, and there was a very simple proof, that this is nothing but a way of expressing the exponential of the Hamiltonian operator divided by kBt divided by Z. And by the way, Z is also equal to the trace of e to the minus h over kBt. Okay? This is very simple to prove this. If you want to show that z is equal to the trace of the same thing appearing upstairs, so this, you can calculate the trace in any basis, in particular in the basis of the eigenfunctions of the Hamiltonian. So, for instance, you can calculate this to be the sum over n of psi n e to the minus h over kBt psi n. But this is an eigenstate of h with eigenvalue En, and therefore this is a very simple thing to calculate. It's just this. Okay? So this object is called the Gibbs canonical ensemble. Normally, it's a quite complicated object to deal with, as always when you have exponential of the Hamiltonian. Nevertheless, in some cases, you can do even exact calculation. For instance, let us apply this machinery to calculate thermal averages when the Hamiltonian is just p squared plus x squared. Okay? So our beloved harmonic oscillator in units, okay, in which, let me put h bar omega in the denominator here. Okay, so x and p have been made dimensionless, but obviously there is an h bar omega in front of everything. So another way of writing this is just h bar omega times a dagger a plus 1/2 in the representation of the a and a dagger. Okay. Very well. Now, notice one thing. What I have to calculate first. Let me first write what I want to calculate. I want to calculate averages. Averages of several things. For instance, I might be willing to calculate the average potential energy. Okay? So one operator that I might want to calculate is this one. Okay? H bar omega over 2 x squared. Average. The other quantity that I might want to calculate is h bar omega over 2 p squared, the average kinetic energy. And obviously, as a result of the sum, I do have h bar omega over 2, the sum of the two pieces, which is the average h, okay? The average energy. Now, this means essentially the following thing. Remember the spectrum of the harmonic oscillator. There is the ground state here with, so the energy divided by h bar omega. The first is 1/2 for n equals 0. Then I have n equal 1, and I have energy 3/2, n equal 2, energy 5/2, and so on. Okay? The difference between all this is 1. Obviously, I'm talking about h bar omega, so in units of h bar omega. Okay. Now, I'm not calculating an average now for a given state. Okay? I want to calculate the average assuming that the harmonic oscillator can be in any of these states, okay, with a probability proportional to the Boltzmann factor, okay? So the probability that, for instance, the harmonic oscillator is in state n equal 3 or n equal any number is simply equal to e to the minus en over kBt divided by z, which is the sum of all the numbers, okay? So this is the individual probability for finding the harmonic oscillator in that state. And then I have to sum overall possible averages taken with the appropriate states. Okay? Is the object clear? The density matrix is made with probability and projectors. Okay? So I'm telling you that the probability that I am in an eigenstate n of the Hamiltonian, these are the eigenstate n. The probability is Wn, read from, well, I erased it, okay, is this. Okay? Now, n before was a dummy label here. Now it's an integer labeling the eigenstates of the Hamiltonian that we well know. Okay? So, is it clear now? Okay, so let us try to calculate something. Okay? The easiest object that we can calculate is, you see, the Hamiltonian apart from h bar omega and this piece is essentially proportional to a dagger a. Okay? So let us try to calculate this object, the average of h bar a dagger a. What it means, according to our definition, it means the trace of the operator a dagger a with the density matrix. Okay? I'll try to go slowly because I understand these are perhaps new concepts. So I'll try to really do every single step. This is according to our general theory as of yesterday.
It's not the trace for the matrix?
Well, it's not important. It could be the trace in a given representation of the product of the matrix, or just the trace in the Hilbert space in any basis you want. Okay? Just the trace of the product of the operators. Okay? Without any reference to matrices. But now I choose a basis to calculate this trace, obviously. The trace I will calculate with respect to the basis that I have written there. Okay? So for me that would be sum over all n from 0 to infinity of the expectation value of the operator a dagger a times the density matrix on the state psi n. Okay? Is this clear? Yep. Which one? Yeah, I mean, if you remember yesterday, I was calculating the average of A as using, for instance, in the first case in which I have a pure state, I was inserting here and here an identity in the form of sum over alpha, phi alpha, and a similar identity here, okay? And with that, I wrote this thing as a trace of the product of two matrices, okay? But you can realize that this expression holds true in any basis, okay? So in some sense, it's really the trace of the product of the operator. You choose the basis that you want to calculate the both operators in, okay? I mean, I didn't make any specific reference to what really this basis was, okay? So the result I got, okay, which was the trace of A times P psi, meaning the two matrices in this basis, you can reinterpret as the trace of the operator A times the operator P psi, okay, where you calculate the trace in every basis you want. Okay? For instance, if I use this basis, this would be the sum over alpha phi alpha operator A P psi phi alpha. Then I insert another identity there, okay, in the form of a sum over another alpha prime of phi alpha operator A phi alpha prime operator P phi alpha. And you realize that in this way, I have now a product of this matrix times that matrix sum over the first and last index, which is the trace of the product of the two matrices. Okay? But in some sense, it's really independent of the basis you take. I mean, if I write it like this, okay, with the two operator there and the abstract operation of trace, then obviously you can select any basis and calculate the corresponding two matrices and perform the trace of the product of the matrices, and you find the result. Okay, but I'm not really limited to a specific basis. In this sense, I sometimes just write it as the trace of the two operators, okay, rather than the trace of the matrices representing the operators in a given basis. I hope this is not a source of confusion, okay? I mean, in practice, then, when you have to calculate a trace, you always select some basis and you try to calculate, for instance, such an object, okay? Then maybe it's useful to insert identities, but sometimes it's not even essential, okay? So in practice, you make reference to a given basis, but in general, the trace of an operator is the sum of the diagonal elements in any basis, okay? And you know that this is independent of the basis if you make a unitary rotation of basis because, well, because two bases that are unitary related don't change the trace. You can prove this, okay? Little exercise. Show that the trace, which means this object, doesn't change if I make a unitary rotation of the basis. Okay, so this is what I should calculate. So to repeat, psi n are the eigenstates of the n excited state of the harmonic oscillator. A dagger A is what appears there in the Hamiltonian, our old friend, and rho is this object here, e to the minus, or if you want this, whatever. I mean, you can choose the expression you like more. Now, luckily enough, in the Gibbs ensemble, which is this, the density matrix is really diagonal in the basis of the energy eigenfunctions, okay? So this thing is simple to calculate. You can watch from this expression also. You see, this is just a sum of projector exactly on those states. Therefore, if you either put this or you just use that, you realize that this object here is the sum over n from 0 to infinity of psi n. This thing acting on this state will give me a factor, sorry, let's put this there, will give me a factor e to the minus en over kbt divided by z, okay? A factor which is essentially this, okay? Times the same state, because it's perfectly diagonal. So all I have to calculate is this matrix element now, which is, however, simple. Remember that psi n are essentially eigenstates of the Hamiltonian also, and the Hamiltonian is nothing but this, okay? So you know how much this is. This is just a number operator, counting how many excitations you have there, okay? So this number is just n. Okay? So it is, for instance, 0 here, 1, 2, 3, and so on. Okay? So the result is that the average of this operator is 0, because you have 0 thing, times the probability of staying there, plus 1 times the probability of staying there, plus 2 times the probability of staying there, plus 3, and so on. Okay? So it's a very simple sum that I have to do now. Let me rewrite it here. The sum is sum over n from 0 to infinity of n e to the minus. Let me write explicitly now the energy to be h bar omega n plus 1/2 divided by kBt. Okay? Divided by the same thing, but without the n. Okay, z. Z is just the same thing without the n. Okay? So the approach to solve this problem is very, very simple. Indeed, you notice that, first of all, you notice that the two sums that I have to calculate are somehow related, right? Because z, let me write it here again, here, is equal to the sum from n equal to 0 to infinity of e to the minus h bar omega n plus 1/2 over kBt. Okay, so this is z in the denominator. In the numerator, I have almost the same thing, but weighted. Each probability is now weighted with n. Okay, so you realize that, first of all, you see that I always have this factor h bar omega over kBt. Reasonable, right? H bar omega is the unit of energy in our problem. kBt is a very important energy scale, the temperature. And therefore, this is a dimensionless quantity which appears everywhere so often that let me call it, let us give a name to this. I don't know, y. X is already too ambiguous. Okay, let me call it y, this variable. This is the energy in unit, the energy of the quantum of the oscillator in unit of kBt. Okay? Good. So let us start calculating things. For instance, I suggest that we first calculate z. If I know how to calculate z, let me rewrite now z as the sum over n from 0 to infinity of e to the minus y n plus 1/2. But the plus 1/2 is really not summed. Okay? I can put it here, e to the minus y over 2. Okay? So this is just the expression I have to calculate. So you realize that if I know how to calculate the sum, then I know also to calculate the sum that I have here is, again, there is a factor e to the minus y over 2, which I can put out. And then I have sum over n from 0 to infinity, n e to the minus y times n divided by the same thing, e to the minus y over 2, sum over n from 0 to infinity, e to the minus y over n. Okay? So if I know how to calculate, first of all, you see that the 1/2 is really irrelevant. They cancels in both things. But the important thing is this. This partition sum, that is essentially the sum of this object, first of all, can be calculated because it's a very simple series. It's the geometric series that is behind this. Second, what appears there is just the derivative with respect to y of what is in the denominator, okay? Which is also quite general. In some sense, what we are willing to calculate is the average energy, which is the derivative of the logarithm of the partition function, pretty much in general. Okay? With respect to the, essentially the inverse temperature. Okay? Y is the inverse temperature. Sometimes one calls 1 over kBt beta. Okay? So you see that taking derivatives with respect to beta or derivative with respect to y is essentially proportional. Okay? In any case, apart from these small details, I hope that the basic math is very clear. Okay, so let us calculate Z. Z is this sum here. I'll do it here, in fact. So this is e to the minus y over 2. This object here is really this to the power n. Okay? This is, I mean, a crucial simplification of the harmonic oscillator. The eigenvalues are equispaced, and therefore e to the minus something times En is really powers of something. This is a small miracle that only the harmonic oscillator does for you. Okay? Now, the sum of infinite powers, you see these are quantities less than 1, luckily, and therefore it converts. It converts to a number which you know by heart to be 1 minus this quantity. Okay? Remember this? The sum of z to the n is just 1 over 1 minus z. This is what I'm using. Okay, when z is obviously less than 1. It diverges for z equal 1. All right, so this is what I'm using here, and that is the result. What about this object here? This object is equal to, you see, minus the derivative with respect to y of the sum from 0 to infinity of e to the minus yn. Okay? I take the derivative with respect to y. I get down a minus n, which is exactly this. I change by a sign, and I get just n. Okay, so since I know this, I've just calculated, is that I can calculate now, where should I do it? Should I do it here? The sum over n from 0 to infinity of n e to the minus yn is equal to minus the derivative with respect to y of the sum, which I calculate to be 1 over 1 minus e to the minus y. Okay? So this object is equal to minus, let's see, the square of this. Then I have to put the minus the derivative of the denominator, which is minus, the derivative of 1 is 0, minus the derivative of this, which is another minus, e to the minus y. You see there is an endless number of minus signs, okay? But all in all, this is just 4 minus signs. So the result is just e to the minus y divided by 1 minus e to the minus y squared, if I'm not wrong. Okay? All right. So since I have now these things, I can try to put both terms in this expression. This drops. So this is e to the minus y divided by 1 minus e to the minus y squared. And here is 1 over, where is it? It's 1 over this thing, okay? Because it's in the denominator. So it's 1 minus e to the minus y. Okay? So I eliminate this with this. And I can rewrite, if I multiply everything by e to the y, as 1 divided by e to the y minus 1. Okay? This is a very, very, very important result. Let me just rewrite it here. The average number of excitations, okay? Remember, average calculating in a probabilistic sense. N is the number of excitation in the states times the probability that I have that state, which is a Boltzmann factor. Average over n is, so if you want, this is the average of the number operator associated to that, is equal to 1 over e to the, let's put back our objects, h bar omega over kbt minus 1. Okay? This is a very, very important function. It is called, in different contexts, the Bose-Einstein distribution function, or even, I mean, it's closely related to the Planck distribution function that you find in the black body. Okay? The Planck distribution function has some factors of omega in front, which come in the black body problem from certain density of states things. After all, you have integral over the case of the photons, okay? The photons have a dispersion which is linear in k, but you have to integrate over the 3k, so you get some k square, and you get the energy in front. So there are omega factors, okay? But apart from that, what you get is just the average number of photons, okay, in a certain state, in a certain of photons of energy omega, or energy h bar omega, is just proportional to this number, okay? Let us look at a bit more to this calculation. For instance, let us calculate the limit of very, very large temperature. By the way, if I know this, I can immediately conclude, for instance, that the average energy is simply equal to h bar omega, the average n, plus 1/2. Okay? So it's equal to h bar omega, this quantity, so 1 over h bar over kBt plus 1/2. This is the average energy of my oscillator. Let's see what happens for very, very large t. Okay? So in particular, I want kBt over h bar omega much larger than 1. It means that your temperature scale is far greater than this amount. Okay? So what happens is that you have this exponential here with a very small e to the y with a very small y. Okay? So you can expand this. I dropped a minus 1. Okay? I can expand this for small value of the thing. Okay? So I have 1 plus h bar omega over kBt plus smaller things which I neglect, minus 1. Okay? So I write here the smaller things. And there is a plus 1/2. Now, this drops, okay? So this is essentially kBt over h bar omega, okay? So the average number of excitations is linear in temperature and kBt divided by the energy. So when I multiply by h bar omega, what I get is kBt coming from here, plus smaller things. Obviously, there is this 1/2 h bar omega, which is the ground state energy, but I'm neglecting even higher, even more important things here from this expansion here. So there is no need to keep this with respect to the thing that I am really forgetting. Okay, so the average energy of this oscillator is kBt, which reproduces very well what you know from classical physics, equipartition theorem. Half a kBt for each degree of freedom, which is quadratic. So there is the result. On the contrary, so if this is the result for large temperature, the result for small temperature deviates a lot from this. So here I have my average energy, and here I have, for instance, let me put kBT over h bar omega. So you see that for very large temperature, this goes like well. Let's divide everything by. So this goes like kBT. So this goes like a thing of slope 1. Okay, if I divide here by h bar omega. Okay, because it goes like kBT. I divide by h bar omega, so it goes like the variable, right? So this is the large temperature limit, slope 1. Then if I continue this classical result down to 0 temperature, I would get the wrong result, that the energy at 0 temperature is 0, okay? And if I apply this thing to the black body problem, I find lots of very, very strange results, okay? So what people didn't know how to calculate in classical terms was exactly this problem. The result which is correct for very large temperature is absolutely incorrect at very small temperature, because at very small temperature, this is a very large object, okay? So this indeed dominates with respect to 1. So if you expand for small temperature, what you have is h bar omega e to the minus h bar omega over kBT. Obviously, you can forget about the 1, because this is much, much larger than the 1. But you shouldn't forget about the 1/2 there, okay? So what happens is that the energy goes like h bar omega divided by 1/2. So it goes to a value here 1/2. No surprise. 0 temperature means essentially the ground state, okay? The ground state has an energy which is 1/2, not 0, the quantum fluctuation. And the deviation from this 1/2, so I can divide here by h bar omega, is described by this function, e to the minus h bar omega over kBT. So it's something like this, okay? E to the minus h bar omega over kBT. So the inverse of this, e to the minus 1 over the variable there, okay? So it goes very rapidly to be just flat to the 1/2, okay? So obviously, large temperature classical result, small temperature quantum result. The crossover is when this quantity is of order 1, okay? So in order to decide in a practical problem if you should consider your oscillator as quantum or classical for practical purposes, just look at what is the h bar omega respect to temperature. If h bar omega is much, much smaller than the temperature, it means that there is no need to perform a quantum calculation. You can just regard it as classical. And the result you will get classically is essentially correct. But if by any chance the temperature is much smaller than the h bar omega, then you should watch out. Quantum mechanics is fundamental, okay? Nowadays, people can do small oscillators. They are called nanomechanical objects, okay? They take essentially cantilevers of very, very small mass, okay? Which have, because of their nanoscopic dimension, very, very large oscillation frequencies, okay? So in particular, you can make very large oscillation frequencies much larger than the temperature with which you hold your nano device. And this means that you can really see quantum mechanics at play in mechanical objects, mechanical oscillator, which have a very large frequency with respect to the temperature, okay? So people have played around in the last few years with those nanomechanical objects, and their quantum effects have to be taken into account if you want to describe the object correctly, okay? You could calculate other things, but this is the essential object. For instance, suppose that I want the average potential energy, okay? So x squared h bar omega over 2. This is the potential energy operator. Then you should expand this in A and A dagger. And you know that this is equal to h bar omega over 2. Then x is 1 over square root of 2 A plus A dagger. Okay? You know this very well, right? Okay. Now, when I expand the square, I have 4 terms, okay? So let me write it. We have done several times. There is a 1 over 2 from the square roots. Then I have A square plus A dagger square plus A dagger plus A dagger A, okay? But you know that A dagger and A dagger A are very related by the commutator. Yeah.
Sir, why the value at exactly t is equal to 0? Is it half the expectation value of the energy in terms of h bar omega at t is equal to 0? Is it exactly half or?
Exactly, yes. Because you have to take the limit. The limit of this quantity when t goes to 0, it means essentially infinite in the denominator, and therefore 0 here. And you reduce just to the
Yeah, the math tells, that is the reason. But experimentally, we cannot reach t is equal to 0. Or can we consider this as a proof that we cannot, I don't know.
There are small deviations from 1/2 at any finite temperature. In other words, there is always, I mean, at 0 temperature, the distribution of probabilities of occupying this thing, the Boltzmann weight, are just 1, 0, 0, 0, everything, okay? So you just occupy the ground state. When you have even a small temperature, it means that this is 1 minus a small quantity. And here there is some small probability of having the first excited state occupied, and an even smaller probability of having the second excited state problem, okay? The probability is essentially proportional to these factors, okay? So these are small factors, which you have to keep including square and so forth to calculate the probability of really having higher excited state. So there is some small deviation from 1/2, but I mean, you see, it's given by this function, okay? So for practical purposes, if t is 10 to the minus 4 h bar omega, this is a tremendously small number.
Is it possible to estimate roughly the deviation, the error?
Is it?
Possible to estimate roughly the deviation at t is equal to 0? I mean, from half.
At t equals 0, this is just 0. At finite t, you have to calculate this number, okay? Which is obviously e to the minus a number divided by something very small. So e to the minus a very, very large number. So exponentially small. What else can I tell? Depends on how large is the ratio of h bar omega to kBt. But this is a very small number in this region here. So this much smaller than 1, okay? Okay, yeah. The formula as written here with the Planck distribution or the Bose distribution function is true for any t. It's an approximation here, which I calculate for large t, and here, for small t. Okay, both are approximations. Which one? This? This? Yeah. Yeah. Yeah.
What will happen if t is equal to log of e times k over h bar omega? But we can see that.
What do you want to do? T equal to? You want to write?
You want to make the denominator equal to 0.
The numerator?
Denominator equal to 0. You want to make the denominator equal to 0. Yes.
No, but this is always greater than 1. I mean,
No, but you can find some t for which.
no. E to the positive quantity. It must be greater than 1. So unless omega is set to 0. But that is a trivial thing. I mean, 0. So the only singularity of this thing is for omega strictly equal to 0, where this is 1 minus 1. Otherwise, if this is greater than 1 minus 1, okay? Nothing, no problem. Is this clear? I don't know if I interpret correctly the question, but there is really no danger in this denominator in this framework. Omega is definitely different from 0, and therefore this is an exponential of a positive quantity.
Okay, what if h bar omega is equal to kbt?
This is e to the 1, e, 2.7 something, minus 1, 1.7 something. Okay? So, kbt equal to h bar omega over log e. Log e is 1. Log of something else? Log of 10.
What if t equal okay, if we want to have
Can I suggest you something?
okay.
Why don't you plot it, okay? Just use some small plotting function and you will see. It's perfectly nice, regular, very, very, very flat here, and goes linearly for very large temperature. In the middle, obviously, if you tell me, what about if t is equal to 3.5? Well, I should calculate, okay? But I see no danger in here. There is no divergence, nothing really bizarre. I calculate the limit for very large temperature, the limit for very small temperature. In the middle, ask the computer to plot it for you, okay? Okay, so I was trying to, yeah.
Here we use the Boltzmann distribution function, right?
Mm-hmm. Yeah.
I mean, why we choose this distribution? I mean,
The natural answer would be ask Boltzmann and ask Gibbs. No, I mean, in some sense, it is remarkable that these people really thought of, I mean, there are some general principles of thermodynamics on how the entropy should be extensive, so you understand the role of the logarithms, okay, and on the contrary, the role of the exponential of the thing. So, I mean, this is the whole history of thermodynamics that gives us this. In some sense, what is remarkable is that I mean, these people didn't care about quantum mechanics, obviously. I mean, it was before the invention of quantum mechanics. I mean, Boltzmann just made suicide close to here, by the way. I mean, before the invention of any quantum mechanics, even the old-fashioned Bohr quantum mechanics. So you might be worried and saying, hey, why do we apply this very, very classical idea? I mean, Boltzmann weights looks like a very classical thing to a quantum object, okay? Shouldn't we apply some Fermi distribution, some Bose distribution to this thing? The answer is no. Forget about Bose distribution. The Bose distribution comes as a result, okay? If you apply correctly the Boltzmann weights to each single state, and you calculate the average number of excitation, you find that that average number of excitation follows a Bose distribution function. But you should not be mistaken and think that what I should put here is some Bose factor, okay? The Bose factor comes wherever it has to come, but as a result of a calculation, not by imposing it. The same would be true for fermions, okay? If I were to calculate some average occupational fermions of some states, okay, I should always use from the beginning the Boltzmann weight. Do the calculation and discover that because of the Pauli principle, very similar calculation, by the way, not so different, except that the sums do not extend to infinity, they're just sum of 0 and 1 because of Pauli. Okay? In any case, by just doing this new sum, you discover that you find the Fermi distribution function. Okay? So in some sense, Bose and Fermi are results that you can derive for a free bosonic system or for a free fermionic system by starting from Boltzmann always, okay? And from the Gibbs distribution, all right? So I'm not going to do now the fermion case because we still don't know many particles, we still don't know what a fermion means, but in principle, a very similar calculation applies to the fermionic case, although with a very different restriction on the number of excitations that I can include, and therefore a different result. By the way, you might ask, why this is boson? I mean, these are just oscillators. This is exactly the same algebra and the same everything that you do for a system of identical bosonic particles. So in some sense, the vibrations of this harmonic oscillator behave as bosonic particles, okay? There is only one particle, is this oscillator, okay? So you might be a little bit worried about what does it mean, bosonic particle. There's only one particle. You talk about bosons when you have many indistinguishable particles with a certain statistics. So it seems strange. Here I have only one particle. But the excitations of these particles, okay, behave as bosons, except exactly as the photons are. The photons are, in some sense, exactly this thing for the electromagnetic field, okay? The electromagnetic field has excitations that are described by a certain number of energy quanta, a certain number of photons. If you ask how, on average, how many photons do I have of a certain energy h bar omega, the calculation would be this, okay? So it would be the same result. And indeed, this is very well used in quantum optics and in all kind of, field of optics. So it shouldn't be, what we have done here is the simplest exercise of a Bose system without even mentioning it. Okay, so much for the talking. Now, let us try to see if we can calculate this. You see that this is equal to h bar omega over 4. Then there are essentially 4 terms, but this term is related to that. I can always rewrite, where should I write? Here. That A dagger is equal to 1 plus A dagger A, because I remember that A dagger minus A dagger A, which is the commutator, is equal to 1. Okay? So I plug it into there, and I have A square plus A dagger square plus twice A dagger A plus 1. Okay? So let us try to calculate now the average of this thing. So you see I have the 1 as usual, simple. This thing, I've calculated the average already, okay? And then I have these 2 other guys, okay? So let us try to see if we can guess what these 2 guys will do. According to my prescription, calculating the average of A square, for instance, means summing over n from 0 to infinity psi n. Then I have to do A square times the density matrix, okay? The density matrix psi n. This I know what it is, usual thing. So this is equal to sum over n from 0 to infinity psi n A square psi n e to the minus en over kbt divided by z, the thing that I've just done before. But before I had A dagger A, and this was giving me n. Now I have A square. How much would this give me? The average of A square. 0, because A applied to psi n gives me psi n minus 1 with the square root of n. A square gives me psi n minus 2, but then I take the scalar product with psi n, they are orthogonal, I get 0. So this thing is just 0 on average, not 0, I mean 0 only on average. And similarly, A dagger square, by the same identical reasoning, okay, A dagger square, A dagger square, A dagger square, it changes psi n into psi n plus 2, and therefore you get 0. Okay? So if I want to calculate the average of the potential energy, which is h bar omega x square, I do have, according to this thing, h bar omega over 4. These two averages are 0. Then I have twice the average of A dagger A plus 1, because the average of 1 is 1. Now, let me just put here the factor 2, and here a 1/2. Okay? So you realize that this is equal to what? This is equal to 1/2. And what you have here is the average energy. I don't know if it is still there. Yes, it is still here. Okay? So the average potential energy is the average energy divided by 2. Okay? In a similar way, you can prove that the average kinetic energy, which is this, there would be some i's and some minus sign, but all in all, there are essentially this thing survive with the same sign, and this have a different sign, but their average is 0, so they don't matter. Okay, so the result is identical. It's still 1/2 the thing. Okay, so the average potential energy and the average kinetic energy are identical and are just equal to the average of the energy divided by 2. You were worried about summing potential energy, and I mean they can be summed as averages, however. Okay, so there's nothing really bad with that. Okay, so the same plot applies, except that I have half of the thing. So for very large temperature, the average potential energy, for instance, is kBT over 2, which is the equipartition. And the same for the kinetic energy. All right? Okay, so from here, for instance, you can calculate the specific heat. The specific heat would be the derivative of the average energy divided with respect to temperature. In thermodynamics, sometimes it's called U. If you calculate this, so the average energy is what I have here. Okay, so this is U over h bar omega. If you calculate it, you see that for very large temperature, it goes like T. So if you take this derivative, you get Kb. And you have the result that at very large temperature, the specific heat is just Kb, Boltzmann constant. This is Dulong and Petit law, I think. Okay? While if you go so if this is the specific heat, So it's KB for very large temperature. If you go down, you have this exponential here, which gives you essentially 0 specific heat. Exponentially small specific heat. All right? So something that has a gap in the spectrum, a very small temperature will show a very important quantum effect, an exponentially small specific heat. While at very large temperature, you wouldn't notice. And you would say, OK, this is a classical degree of freedom, so KB per degree of freedom. OK? KB half. All right? So the signal of quantum mechanics is in this freezing, okay, with this exponentially decaying things for very small temperatures. And with that, with this ingredient, you can calculate, for instance, the specific heat of a solid. Okay? You know that the solid is an assembly of oscillations, okay? For very large temperature, they all behave as essentially classical oscillators, and therefore is KB times 3, really, because it's 3-dimensional per n the number of particles, okay? The specific heat of a classical gas or whatever. For very small temperature, there is this things that come into play, but you have to remember that the phonons have a branch with energy that is going to 0. So there is in the integral, you have to integrate now over omega as well. And in the integral, you have to weight the density of states and so on and so forth. And probably you have done in solid state something like this. You know that you can derive the Debye law, for instance, for the specific heat of a solid. The ingredient is exactly this, but it should be integrated appropriately. So the same ingredient appears in many, many instances, in the black body, in the Debye law of specific heat of a solid, in lots of quantum optics and so on and so forth. All right? So this is a very, very useful object. Do you have any other questions? Yeah. What? It is. It is. The question is the trace an abstract object that works even in an infinite dimensional space? Yes. Okay. I mean, don't ask me the mathematical subtleties of this thing. Obviously, for a general Hilbert space, depending on the basis you are willing to use, it might be complicated to control every single element of this calculation. But generally speaking, I mean, what we have done is an infinite dimensional Hilbert space, okay? Very innocent, okay? A single quantum oscillator, but is an infinite dimensional space of functions, okay? Which we have studied in a very nice basis, which is this, Hermite polynomials times Gaussians, okay? You can expand any function from minus infinity to plus infinity in this basis. Now, a trace in this basis is calculated by simply summing over the element of the basis, okay? If I of the identity, well, obviously, one has to be careful. I mean, some of the quantities can, I mean, thanks to this, okay, if I want to calculate the average of the identity, there is no problem, because this is simply equal to the trace of rho, and the trace of rho is 1, okay? So in some sense, there is always a denominator that takes care of making everything equal to 1. And this denominator is the partition function, which is an infinite sum. So you might be worried, can I calculate, is it, I mean, it's an infinite sum that in principle is a delicate object. Sometimes not even simple to calculate. Actually, most of the time it's very complicated to calculate. Okay?
What if we use, instead of the weight function, which is Boltzmann, just 1, and then if we try to calculate the trace of the number operator A?
So the trace of the, in other words, the trace of the number operator,
Yeah, with the weight function 1.
this thing, so of A dagger A without, without the row?
Yeah.
Oh, well, this is not defined.
It's not defined.
No, it's infinite, okay? I mean, the definition is sum over n from 0 to infinity of psi n, A dagger A psi n. But this is n, okay? So it's the sum from 0 to infinity of n, which is, I mean, infinite. So sometimes those traces, although perfectly in principle defined, are divergent, you know, for some operator. So I do not guarantee that any operator that comes to your mind, okay, has a trace that is finite. But if you calculate physical quantities, usually things tend to work, okay? So unfortunately, this is not a physical quantity. It's a trace of thing. I mean, if you put here a row, immediately is a physical quantity. Is the average on the thermal state of the number of excitations. And here comes the Bose distribution function. Perfectly meaningful and, okay? But if you calculate the trace in the infinite dimensional Hilbert space, it might be, I like finite dimensional matrices, where a trace is always a finite number of terms, okay, and therefore is always finite. In Hilbert spaces, you have to be careful. Sometimes things tend to diverge because of an infinite number of terms, okay? There is also a curious thing about hydrogen atom. I mean, if I calculate the thermal effect with the hydrogen atom, for instance, suppose that I want to calculate Z, okay, equal to the sum over n, okay, over the states of e to the minus en over kBt. Okay, first of all, there is obviously in this sum I should include also the extended states, okay, the states where, I mean, the hydrogen atom is not bound, which have positive energy, which you might say, okay, maybe this will make a small contribution. Yes, but there is an integral over a very large thing. Forget about this, okay? Suppose that I just limit myself to the bound state energies, okay, the En that are negative. Then I know that for every n, I have several states. There is some degeneracy. But apart from degeneracy effect, which I can count here, I have something like sum over n from 1 to infinity of the degeneracy of the state, which it's 1 for 2 for the ground state, it's n squared. I think it's n squared. I mean, you can count them. It's e to the minus, say, Rydberg divided by n squared divided by kBt. Okay? So you realize that as you go to very, very large n, unlike the other case where this thing was e to the minus n, large number, this becomes essentially 1. Okay? So you see immediately there is something bizarre. I mean, the accumulation of energies now in the hydrogen atom towards 0 makes the formal expression for the partition function diverge. Okay? So, I mean, in principle, one has to cure this. The hydrogen atom is a bit delicate in that. Okay? I end this discussion here. I forgot what is the solution to this problem, in fact. Okay? Maybe you can think of it. Okay? There must be a way of making physical sense out of the hydrogen atom at finite temperature. So think of this. It's just to remind that the sums, certain times you look at them and they are kind of tricky. Okay. Obviously, if, for instance, this is in the denominator and there is in the numerator something such that I can make sense of the ratio, then still things are kind of reasonable, okay? But, I mean, I just give it to you as a puzzle. Okay. What comes next? Well, we have exhausted some of the basic exact quotation mark facts of quantum mechanics, and now comes a whole chapter which has to do with approximate calculations. I mean, as you have seen, there are a few problems that one can do exactly. Oscillators, hydrogen atom, square wells in all possible forms, delta functions. But, I mean, if I give you a potential, chances are that this potential is not exactly solvable, and therefore you have to do something. For instance, I can give you, even as, I mean, a potential that is quadratic plus a cubic term, or quadratic plus a quartic term, okay? So a perturbation of the harmonic oscillator. What do you do? How do you calculate things? You have to develop some perturbative scheme, okay? So assuming that the perturbation is small in some sense that we will discuss, you should have some way of calculating some power expansion of the physical results, okay? So the first, I will just set the basic problem. I will really not go into any details because it's too late to start a new thing. So what we'll do next time is to start doing perturbation theory, which must be settled in two possible ways. First of all, we will study this problem. Remember how to study the eigenfunctions of energy E of a certain Hamiltonian, okay? This is called time-independent perturbation theory. In some sense, it works without the time, just in the time-independent Schrödinger problem. And the problem is that H is some H0 plus some perturbation, where I suppose I know everything of H0. So I know the eigenstate of H0, the eigenvalues, everything, okay? So I know how to solve the unperturbed problem. Let me set the notation here. Okay? So phi with this 0 notation are just the unperturbed eigenstate of H0, which is only a piece of the Hamiltonian. And similarly, E0 is the energy associated with it. Okay? So I want to use this, for instance, as a basis to expand things. And I would like to solve this problem. For technical reason, essentially for counting purposes, it's good if I put a lambda in front of a v. In this way, every time I see a lambda, I remember that this is coming from the v. And so I can think of expanding everything in terms of lambda, okay? So the result I would like to do is to find new states now, let's call them phi n of lambda, such that H0 plus lambda v is equal to En of lambda times phi n of lambda. Okay? So this is the problem I would like to solve. Is this clear? This is the perturbed Hamiltonian. These are states that I should find, okay? And these are energies that I should find. And the goal that we will tackle next time is how to write down power expansion of all these quantities, okay? So I will try to write, for instance, this as En0 plus lambda some first order perturbation plus lambda square some second order perturbation, and so on and so forth. And similarly for the states, okay? I expand the state as this plus lambda, the first order correction, and so forth. And I will try to make the equality work, okay? So I try to find formulas to express all these corrections to the energies and to the states in terms of appropriate matrix element, okay? So this will be what we will do next time. And later on, we will do another problem, similar, but now I will tackle this problem. So the time-dependent problem, where I have some h0, which I know, plus some perturbation, okay? Again, let me put the lambda, psi of t. So how to study this problem if I know a lot about h0? So a small perturbation of h0, sometimes with a field that is not necessarily constant in time. For instance, I can put some electric field which oscillates in time, some magnetic field, some external potential, okay? So this demands for a solution of a time-dependent problem, which, however, I want to tackle in a perturbative way, because I assume that most of the Hamiltonian I know how to do, and this is only a small effect, okay? So I should develop also here a perturbation strategy similar to this, okay? But in the end, it's even simpler than that, okay? So we will see that the strategy is even simpler. Okay, so I would say that this is just the goal of the next few lectures. We will do a few exercises on practical examples, oscillators perturbed in different ways. We will, among the exercises we will do with the strategies, I regard as pretty interesting at least two of them. One is to calculate what is the change in energy if you have two atoms, okay, two hydrogen atoms, for instance, which are far away, okay? So each atom, you would know how to calculate. The ground state is minus a Rydberg, okay? I ask you now, if you put two atoms a certain distance away, what would they do? Would they attract, okay? In other words, what would be the total energy as a function of the distance? And we'll try to calculate this effect, and we will discover that there is an attraction between these two neutral objects. This attraction is called van der Waals attraction, okay? So even if the two atoms have no charge, so you might say, okay, well, just zero attraction. Well, no. The fluctuations of the positive and negative charge there generates fluctuating dipoles that somehow communicate to the other guy, and the other guy likes to put his dipole in a kind of nice location with respect to this dipole. So they fluctuate in a cooperative wave in such a way as to reduce the energy, okay? And this is the origin of van der Waals, and we'll do this in second order perturbation theory. And another exercise that's quite interesting is using the spin orbit piece of Hamiltonian plus the corrections to the kinetic energy to calculate the fine structure splitting of the levels of hydrogen, okay? That again is an exercise that requires using perturbation formula. And you find small splittings proportional to the fine structure constant, which in principle can be tested against experiments, okay? So these are the two most important, although there will be other simple ones.